I had a little surprise for you in the last video, and I didn't tell you there was a surprise coming, but there was. So let's do some practice, some examples on discrete random variables. So first off, the example claims that this is a probability model. All right. And it says it describes the number of repair calls that an appliance repair shop may receive during an hour. So usually there's either 0, 1, 2, or 3 or 0, 1, 2, or 3 calls. And there's a chance of each, right? There's a 10% chance that they don't receive any calls in that appliance repair shop in an hour. There's a 30% chance that they receive one, a 40% chance they don't receive any, and Jason, the table's not complete. What are we gonna do? Well, don't worry. We know things about probability distributions. Each probability has to be between 0% and 100%. And all the probabilities have to add up to 1. So to complete this table in part A, just figure out what do we need so it adds up to 1. So 0.1 plus 0.3 plus 0.4 plus whatever this is. Let's not call it x. X is many other things in this problem. Let's call it, choose any variable you want. I'm going to choose the variable smiley face equals 100% or 1. Any variable works. Smiley face can be a variable. We can use English letters. We can use Greek letters. Let's use a smiley face. Well, if we simplify and solve this equation, it's going to be 0.8 plus smiley face equals 1, and subtract 0.8 from each side to get that smiley face is equal to 0.2. There we go. And now we got a probability distribution. Part B. How many calls should the shop expect? Expected value. I don't know what I'm doing with my glasses there. And then make sure to include the units. The units are always going to be the same for the random variable, the mean, and the standard deviation. My hands are really just going off the rails today. So this is our expectation. So remember, the expected value is look at all the values, multiply them by their probabilities, and then add them all up. And you might want to use a spreadsheet. You might have used a spreadsheet in the previous video. You can reuse the same spreadsheet once you kind of get it constructed. So if you haven't kind of filled in an outline here, I'd highly recommend pausing the video and doing it now. This time, our x's and our p of x's, these are going to be different. I don't know, maybe we'll put a different color because these are going to change every single time. Now x's, it's no longer cups of coffee. Our x's, right? These are our x's up here, and the probabilities for each of those are below. So our x's are just 0, 1, 2, and 3. 0, 1, 2, and 3. We don't need this fifth one, so let's get rid of it. What are the probabilities of each of those? 0.1, 0.3, 0.4, and 0.2. There's no probability for the last one. Right, we're only dealing 4 things, so make sure that we only have 4 things here. And now look, all of our calculations from before, just like that, are already done for us. Okay, which is why computers are nice. So multiply each of the x's by p of x. Let's just look it over and make sure that, yep, that's multiplying them all out. Add them together. That's our expectation. That's our expected value, 1.7. And there we go. Just multiply, 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 multiply. Add all of those answers together. That's your expected value or our mean. So how many calls should we expect? About 1.7 calls per hour. And sometimes it makes sense to round. Sometimes it makes sense not to. Here, I think it makes sense not to round. Closer to 2 calls per hour, but sometimes 1 call per hour on average. And to calculate the standard deviation, again, we have all these sets, all these steps. The standard deviation is just the square root of the variance. And the variance, sigma squared, is just, this one had a lot. First, we said, how far is each thing from the mean? What is the deviation of each value from the mean? We wanted that positive, so we squared it. We scaled it to the probability, so we multiplied by the probability, and then we added them all up. This is the formula from the previous video. But we've already done that, right? Look at, these are all the average deviations from the mean. Click on it, you see, yep, it's taking orange, subtracting purple, that's good. Yep, orange, subtracting purple, these are all the deviations from the mean. Yep, we're squaring it, still squaring it, still squaring it. We don't need this bottom row, we only have 4 things. Great, so that's the deviation squared. And then here, I can zoom in, that people can actually see a little bit more. You don't have to get out your binoculars or whatever to look at this. Magnifying glass. That's the word I'm looking for. Nice try, Jason. All right. Wait, can I not? I can't click it up only one. All right, it's fine. And then we just multiply each deviation squared by its probability. Yep, that's working well. We're adding them all up together. This is our variance, 0.81. Our standard deviation's 0.9. Square root of 0.81 is just 0.9 calls per hour. Same units. So again, the interpretation here is that on average, we get about 1.7 calls per hour, plus or minus 1. Okay? Usually we'll be within 1 call of 1.7 is the interpretation of this. Okay? And again, standard deviation and what this represents and how many things lie within standard deviations is going to become a very big theme for the next unit when we talk about the normal distribution. Okay? So let's, look at some more stuff. What's the probability that we get 2 repair calls? How do we write that? The probability that the number of repair calls that we get in a single hour is equal to 2. That's how we write this. And we just consult our table. What is the probability that X is 2? 40%. And again, I will accept either answer. I love percents for probabilities, but some people prefer decimals. Let's pause a moment. Try to do the rest of these on your own. Okay? Pause the video. Do E, F, and G on your own, and then let's see if we get the same answer. The probability that the number of calls is at least 1. Again, at least means greater than or equal to. Probability that they get at most 2. At most 2. At most means less than or equal to. What's the probability that class, not classy having a typo in the notes, Jason. What's the probability that they get less than 2 repair calls? Strictly less than 2. Well, so this is going to be the probability that they get 1 plus the probability that they get 2 plus the probability that they get 3. At least 1 is all 3 of these together. They're disjoint. They're mutually exclusive events. You can't have 1 call and 2 calls in an hour, in the same hour. It's one or the other. So just add the probabilities for 1, 2, and 3. That's 0.3, 0.4, 0.2. Which adds up to 0.9. It's very likely that we're going to have at least one repair call in an hour, which is good because we're a repair call shop or repair shop. If we're not getting any calls, and I don't think our business is doing too good. Now we can do the same thing for this, right? This is going to be the probability that x equals 0, probability x equals 1, plus probability x equals 2, which is 0.1 plus 0.3 plus 0.4, or 80%. This one over here is just probability x equals 0 plus the probability x equals 1. 2 is not included here. It's strictly less than 2. 0.1 plus 0.3 equals 0.4. Unless I copied any of these numbers down wrong. 0.1, 0.3, 0.4, 0.2. This should be what we have. Or 40%. That's this example. Let's do another example. Again, it can be a good idea to pause the video, try to do the example on your own, and let's see if we get the same stuff. All right, so we're rolling a die, and if it comes up as a 6, this sounds familiar. Well, not exactly the same, but you win $100. If not, you get to roll again. If you get a 6 a second time, you win $50. Otherwise, you lose. This one's more complicated, right? This probability distribution's complicated. What are the options? Well, we need a random variable. Let's call our random variable x because we're not very creative. Well, maybe you can go back to the smiley face. Let x, right? This is what we want. We want a probability distribution for the amount that we win. So let's just say the amount that we win is x. That's what we care about. The probability of that. So let x be the thing that we care about. Let x be the amount won in dollars. And it wants a probability distribution. So that is, what are all of our x's? And what are all the probabilities of those? We usually use capital P. So let's make a table. And in a lot of the book's examples, they make the table horizontal. You can also make the table vertical. You can have a table. You can rotate your table any way you want, as long as you don't flip it upside down. That'd be weird. But table can be this way or the other way. Same table. So what are the outcomes? What are the possible outcomes? Well, we can either get $100, or we can get $50, or we can get $0. Those are the only options. 100, 50, or 0. You can even order them. Smallest to biggest, that'd be even better. I'm not going to require you to reorder this. But it looks a little nicer if it is ordered. This is not worth points to me. And the probabilities are more complicated. So let's just kind of go in order. If you roll a 6, you get $100. So if I'm rolling a regular 6-sided die, what's the chance that I roll a 6? Well, there's 1, right? What's the probability of rolling a 6? Well, there's 1 favorable outcome divided by 6 total outcomes. So the probability is 1/6. So if it comes up as a 6, we win $100. So the probability that we win $100, so the probability that x is $100 is just this 1/6. So we can have as a fraction because this as a decimal isn't exact. But you can also, right, 0.16 repeating works, 16.6 repeating works, for 16.6% with the 6 repeating also works. A couple of ways that you can write your answer here. And if not, this is a key critical phrase. If not, you get to roll again. This has to do with conditional probability. And this says that if this doesn't happen, then we roll again. And so this is where things get a little interesting. So next, we have to roll a 6 a second time. So what is this? The second one has to do with what is the probability that we roll a 6? Rule? Come on. What's the probability that this first thing doesn't happen? Right? Roll not a 6. And then, this is going back to our probability unit, last unit, we have something happen, and then something else happen. Okay? And it's conditional probability, but they are independent. So we have to roll. So for $50, we have to roll not a 6, and then we roll a 6 afterwards. So 2 rolls of a die are independent, right? The die doesn't remember where it fell last time. We're shaking it around. We're not being that dishonest person that rolls the die and like doesn't actually roll it, right? So first, what's the probability that we don't roll a 6? There's 5 ways to not roll a 6. And then, because these are independent, we can multiply by the probability that we do roll a 6. This is going to be the way that we win $50. 5 over 36. And again, this is because it's independent. Otherwise, we'd have to use conditional probability. All right. So it's sort of related, but because they're independent, I don't really want to leave that note up on there because it's a little misleading, even though it is correct. You can ask me more about that if you want. So this is how we can get $50. Don't roll a 6 the first time, 5 out of 6 chance of that. And then roll a 6 the second time, 1 out of 6 chance of that. They're independent. You're going to get 5 out of 36. Or, I don't remember what that is as a decimal. 13.8 repeating percent. And for 0, there's 2 ways of filling in the last thing of this table. The first way is to just say, well, it's whatever percent's remaining. Or you can do the same logic. Just like we did in the previous example is one way to finish this off. But let's double check our work. Let's go over here. What's the probability that we don't get a 6 twice? Well, that's probability, 5/6 twice. Multiply them together, they're independent. And it's an and, multiplication, I don't know. You get 25 over 36. Or, write this as a decimal. Should be 5 times that other thing. I'm not going to do it in my head, though. 25 divided by 36 is 69.4 repeating percent. All right. We have a probability distribution. Do these add all up to 100%? Hopefully. 25/36 plus 5 is 30/36. 1/6 is another 6/36. That's 36/36. That's 100%. That's 1. Great. This is a probability distribution. Each probability is between 0 and 1, 0% and 100%. And they all add up to 1. Excellent. The expected value of our x, otherwise known as the mean, mu, is multiply each x by its probability and then add them all up together. Luckily, we can use our spreadsheet. This time we only have 3 options. We either win $0, $50, or $100, and the chances are 25/36, 5/36, and 1/6. As a side note, you might want to move this over here and also check, sum up everything in the probability. This should always add up to 1. If it doesn't equal 1, we did something wrong. All right, this thing above here, that's the expected value. And this thing above here is the variance. And this thing above here, I really don't need to spend time making the table look nice, but it's a good idea for you if you want. All right, those are little arrows pointing to what's above. You can also do borders and stuff, but I'll hold myself down. So the average, again, we're just multiplying, double check, multiplying all the x's by their p of x's, good, and then add them all up. The average is 23.61 repeating. So on average, we win $23.61. The units here are the same as the units for x, and x is the amount won in dollars. Find the standard deviation. Standard deviation sigma is going to be, well, we already did it. Right there. You can double check that the calculations are still correct. You can delete this row. Doesn't actually change it in this case. It only matters over here, but you can delete the row to make it look nicer and be real confident that you don't have anything bad. Standard deviation is about 38.16, approximately. 38.16. The units are also in dollars. All of these have the same units. X, the mean, standard deviation, same units. So what does this mean? This means that on average, we'll win about $24 plus or minus $40. And again, standard deviation in this interpretation, this logic for what I'm saying, makes a lot more sense when we have more complicated probability distributions. Obviously, if there's only 3 outcomes, we know what to expect. But when there's a bunch of outcomes, that standard deviation becomes much more helpful. If a standard deviation is big, that means there's a lot of variability in the outcomes. If the standard deviation is small, that means you're pretty sure what you're going to get. You're pretty sure you're going to be around something. So here our standard deviation is pretty big. There's a pretty big difference in these outcomes. Okay. Should you play the game if it costs $25? On average, you're going to win $23. So if it costs $25 to play, you're probably going to be losing on average. Okay. The profit is your win minus the cost. Minus the cost. Minus the cost. So here, our average profit for us is our average win, which is, right, 23.61 minus the average cost. Well, the cost is the same every single time. Our average profit here is going to be about $1 negative. Uh-oh, that's not good. Negative $1.39, I think. We subtract this out. If I did my math right, otherwise there will be a little edit right there. I did it wrong. So on average, we lose $1. Oh, no. You shouldn't. Maybe you want to gamble, but you're unlikely to. The odds are against you, just like all gambling. Say no. On average, you would lose $1.39 per game. So if you played and got lucky, you could win. But if you played it a lot, eventually you're just going to start losing. So how would this be a fair game? Well, it'd be a fair game, right? If the average profit equals 0 So when does this equal 0? Well, if it costs the mean. Right, so if it cost the mean, which is 23.61, and there's a little rounding, so this is technically not completely fair, but rounding error aside, this would make it fair. All right, that's the examples video on discrete probability. Next, we're going to get into a special kind of discrete random variable called a binomial variable. I don't know how to stop recording this video. I've recorded so many videos and I can't find my mouse, but I found it now, so we can actually say adios.